Okay, we've got two groups of students. We've got 9 in group 1, 7 in group 2, and we've got their marks. And we want to do a test to see whether there's a distribution between the mean marks of the two groups. Okay, so presumably we're regarding these as being samples from wider populations. And it says, oh, are we going to do a t-test? All right, so what assumptions do we need to make? Well, this is a two-sample t-test. Okay, and with all t-tests, okay, we might have to use a t-test when we've got a small sample and we're not given the population standard deviations. So that's why we have to, but they're not the assumptions we need for us to be able to. For us to be able to use a t-test, this is all in your notes. And we've also been discussing this a lot with some of the project work we've just been doing about reaction times. For any kind of t-test requires the parent population or populations to be normal in context. So we have to assume that the marks in group 1 are normally distributed and the marks from group 2 are normally distributed. Okay? Or the wider populations they're drawn from. Don't like this question because it should be clear these are samples from populations. Okay, but not populations being normally distributed is first assumption. But for our independent sample t-test, you also need to assume that the variances of the two populations, we don't know the variances, they have to have the same variance as each other. So the unknown variance must be the same for each population. So those are your assumptions for a t-test. Okay, and then we're not going to do a t-test, we're going to use a distribution-free test, okay, to decide whether or not there is a difference. So we have independent samples. Distribution-free tests, well, we could use a sign test, except we can't, because sign tests only work with matched pairs data. I don't have the same number of observations and they're not matched up, so therefore I can't use a sign test. It's got to be one of the Wilcoxon ones. The Wilcoxon sign rank test is again for matched pairs, so it has to be the Wilcoxon rank sum test. So I have to rank all of these marks from the lowest, which will be 18, up to the highest. Okay, are there two 35s? Yes, so they are going to be tied ranks, 16 students in all. So the last two ranks, 15 and 16, are going to have to be shared. 15.5 and 15.5 are going to be the last two ranks. You fill in all the ones in between and you total the ranks for each group. Okay, and then you perform the process where you have to take away a half times n times n plus 1 and get your statistic. In fact, you should get the two statistics, two values, a high one and a low one from the two groups. Okay, and you can use the check given in the formula book to make sure that if you subtract 1 from something, m times n, you get the other one. Okay, so you then use the rank sum critical value tables from your formula book to see whether your low end critical value is significant. We only ever work with the smaller of the two, okay, and we're only looking for a difference, so we're going to do a two-tailed test, and that means that we can select whichever of the two measurements turns out to be the lowest one. We can always use the low end one. So to see how that works out on the mark scheme, okay, here are assumptions, as said. I didn't state your hypotheses, but that's what it should be. Okay. And then these are the numbers you should get. So when you rank as a single group, then you should find that you get totals of 33 and 103, and when you convert them into U statistics, the low one is 5 and the high one is 58. Critical value from your table is 13, so we compared the 5 with the 13. It's the low end one, so that is significant because it's below the 13. So we reject H0. There is evidence that the groups of students have different mean marks, and those underlined words must appear in your conclusion. So that was question 8.